Okay, good. Yeah. Thank you for the introduction. Yeah, today I'm gonna give you some more information about stickiness, and in particular, stickiness with their main application in BHV phylogenetic tree spaces. Um, so yeah, so phylogenetic trees are used in biology to represent evolutionary relationships between species. And we now want to treat these trees as mathematical objects in some suitable metric space. And there are a couple of candidates, and today we're going to focus on the Billera-Holmes-Volkmann BHV phylogenetic tree spaces. So, and now if we have such a metric space, we can now do what Susanna's already talked about. We can now start to compute means of a set of given trees. And yeah, as was already talked about, if we have a distribution with a finite first moment, we can indeed define this, what we call the Frechet function down here. Note there's a slight difference to before. We rescale with factor a half, and also we subtract this second term here, which is arbitrary. We do that for an arbitrary y. This way we can, due to the triangle inequality, get away with just the first moment of the distribution for this integral to be defined. And then now the Frechet mean set is given as the set of minimizers of this Frechet function. So, and as was alluded to earlier, this Frechet mean can exhibit some non-standard behavior, and again we're gonna focus here on the phenomenon of stickiness, and I hope to now give you some intuition on that. So we go back to this tripod or three spider, or the BHV space actually of phylogenetic trees with 3 leaves, and we now put a point mass all with equal weight on each of the legs of this spider thing, and all of them with distance 1 to the origin of the space. And as one would assume, the Frechet mean then lies just at the middle. However, this weird construction of the space causes some weird behavior if we now start to move a point and fix the others. We can actually vary it slightly. So here we increase the distance to 1.5, and the Frechet mean still lies at the origin, which of course you wouldn't expect that on the real line. So what this kind of means is that the stickiness somehow represents that the Frechet mean of the distributions is robust against some slight changes. And what this also means is that it kind of makes it hard to approach two-sample problems like classically with something like a t-test to discriminate between the distributions based on their mean. So to go back to BHV spaces, so some previous work has focused on central limit theorems in these BHV spaces, and this is basically what people have done before on stickiness. Then it was always like with focus on a single space, and but at some point people introduced some more general concepts how this stickiness phenomenon could be rigorously defined, and we called it here the sticky flavors. And in fact, we've shown in our paper that in the case of BHV phylogenetic tree spaces, you do indeed have that all of these flavors are mostly equivalent. And furthermore, we wanted to try to tackle the problem that you can't really discriminate, or stickiness makes it hard to discriminate between distributions based on the mean, if both distributions are sticky. So maybe let's talk a little bit about the BHV phylogenetic tree spaces. So we denoted by Tn the the space of rooted and labeled trees with a fixed number n. And what you have with these trees is, as we've seen before, these interior edges, people call them splits, characterize the so-called topology of the tree. And a tree can have at most n minus 2 of such splits, and these trees are then called binary. And the idea in BHV spaces is that you assign each binary topology just a Euclidean orthant, and a tree with that topology is then the position of that tree in that with that topology in that orthant is then just determined by the length of the splits. And what you then do is, okay, on the boundaries of these orthants, there's some overlap, resulting in the same non-binary topologies of trees, and then you just glue them together. And with these spaces where you actually glue them together are the interesting parts for stickiness, and we will refer to them as strata of a certain codimension. And yeah, as we've seen before, this would be the T3 case for trees with 3 leaves. And in the case that you have 4 leaves, it now becomes more messy. You have basically lots of these book-like structures that are glued together. And as you can see here, in this case, we have this half line, which corresponds to this topology, which is on the same boundary of these 3 binary topologies. And this is actually where now stickiness can happen. So you might have that the Freshemin might not necessarily stick to a point, but it sticks to this lower dimensional subset here, this stratum. And exactly, so maybe since it's a metric space, we might also want to talk about the distance. So inside these orthants, it's just the Euclidean distance. And to go from one topology to another, you kind of have to delete and add splits of the tree in kind of an optimal fashion. And you can actually do this in polynomial time to compute geodesics in the space. Spoiler. And so this space is kind of nice. However, it doesn't have a smooth structure due to this gluing. However, it's still nice enough to be, so you are able to compute lots of stuff. And as we talked about, it's a cat0 space, or a space of global non-positive curvature. So yeah, roughly speaking, we have that the geodesic triangles in our space are smaller, quote unquote, informally speaking, than triangles with the same side lengths in R2. So for us, as the decisions, here now has a couple of nice properties as a Hadamard space. So you have that every probability distribution with a finite first moment has, in fact, a unique Freshemin, so we don't have to bother with Freshemin sets with more than one element. And also we have that any 2 points are joined by unique minimizing geodesics. And also we don't have nice tangent spaces, vector spaces at each point, but we can still do something similar in these spaces. So if you now take 2 geodesics that start at the same point and plug basically them into the Euclidean law of cosines and then let the t go to 0, you actually can compute in Hadamard spaces an angle between 2 geodesics. And so this now, if 2 geodesics have an angle 0 between them, you can think of them as a direction, and this gives you equivalence classes of geodesics. And the space of these equivalence classes is then denoted, we denote by sigma s, is then called the sigma x, and it actually becomes a nice metric, rather nice metric space itself, even though it kind of inherits some not so nice properties, but it's still good enough for us. And for our case here, we deal with BHV spaces, and especially we want to look at these lower dimensional strata. And in these strata, you can actually decompose your space of directions at each point into a spherical join of directions that are kind of corresponding to points going through the stratum, and also ones that are perpendicular. And for the study of stickiness, the perpendicular ones are the ones that will be interesting. So in this case here, we still have this book-like structure, and your perpendicular directions would, at the point mu, would then just be these three here. And now we want to talk about about stickiness and what these stickiest flavors are. And so we introduce a couple of different concepts that would kind of describes this phenomenon of stickiness. And exactly, so we now fix distribution P and a stratum S. And the first flavor that we're talking about is called, we call it Wasserstein sticky. So the basic idea is that, okay, we now have that distribution P is Wasserstein sticky if we construct an open ball around it in the Wasserstein space, such that any other distribution that is contained in that environment has a Fresnel lying on that stratum. So you can vary the distribution in the Wasserstein topology. The next one, we call it perturbation stickiness, which also we want to perturb a distribution, but this time we only do it with by convex combination with some point masses in our space. So it's kind of, we don't suppose as much apparently as with the Wasserstein case. And maybe the one most interesting for statisticians, we call it sample stickiness. And sample stickiness is if you have now a sequence of random variables following our distribution P, and then after some time point when you sample and compute the Fresnel mean, your Fresnel mean starts to get stuck at the lower dimensional stratum and won't leave it anymore. So you have this sticking, your sample mean sticks to the stratum. Exactly. So, and kind of the main tool in the BHV spaces or Hadamard spaces that we can use, we don't have nice smooth structure, but due to convexity properties, we can still compute directional derivatives of distance functions. And this way we can also do that for our Fresnel function. So the idea here is just, okay, we take a direction and a representative of set direction with unit speed, plug it into the Fresnel function and differentiate it at 0. And this gives us directional derivatives. They exist, are well defined, and we even have a nice formula for them. Basically, we integrate over something like an inner product with a unit direction, and we denote this by phi. And now, if we have that, we can state this theorem here that, in fact, in BHV phylogenetic tree spaces, all these three flavors of stickiness are mostly equivalent. So you have equivalence. However, in the case of sample stickiness, you kind of need to assume something on the support of the distribution. Basically, what this assumption 1 here tells you is that you should be in a suitable BHV space. You shouldn't add additional leaves to your space that are kind of redundant, so that your distribution doesn't live in a subspace of the space. And if that is fulfilled, you do indeed have the equivalence of these three definitions, and these are tied to the condition that your directional derivatives at this population mean of the function are all strictly larger than 0. And now we have these directional derivatives here are a very nice tool and kind of allow us to interpret them. So what we would say what these directional derivatives kind of convey is how resistant this direction is against how resistant the Fresheimian is against moving into that direction. So we just gave them a name. We call these directional derivatives here the degrees of stickiness. And our idea is, okay, now we inference based on the Fresheimian might not really be reasonable in a case, but still we can do some testing based on these degrees of stickiness to discriminate between not the means, but something that is related to the mean of two sticky distributions. Yeah, and so we actually work with a data example of both 63 trees each. These trees were inferred from the same data, however, using two different methods of inference. And then what ended up happening is that, okay, both of the samples do have rough the same mean, or mean very, very close to each other with the same unresolved topology. So this is how the tree of these data examples looks. So we can't really say a lot about the relationships between these species here. We only have a couple of splits that seem to be present. And yeah, what we then did, okay, we would like to test the hypothesis that the directional derivatives or the degrees of stickiness of these two distributions are the same. However, the space of directions is still pretty nasty. It inherits lots of not so nice properties about BHV spaces. So we decided, okay, we propose to work with some finite selection of directions. And since, due to the trees being inferred from the same data, we had a natural pairing for the trees. And so what we did is, okay, we performed just a classical t-test now for each direction. And then afterwards, we do a home correction. And yeah, and this, in our case, resulted in a statistically significant p-value, reaffirming previous results on the data set. Okay, yeah, then maybe some outlook. So hopefully in the next couple of weeks you find on archive something more about stickiness, mainly stickiness in general, kappa spaces, and we focused on Wasserstein topology. We compare stickiness there with respect to different topologies. We kind of tackle the problem, okay, where in these spaces, how nasty does the space have to be to stickiness be a thing? And also we cover some stuff on convergence rates of the expected distance of the sample mean to the population mean. Okay, yeah, thank you for your attention.
Thank you for the presentations. Are there any questions? Yeah.
Thank you for your presentation. I was just wondering, you probably said it, but do you have an explicit expression of the Fresheimian on BHV spaces? Or?
No, unfortunately not. You have to solve it by some stochastic algorithms. There is not yet an upfront way to just directly compute the Fresheimian. However, there are some stochastic gradient descent like things that you can do to compute the mean.
So you optimize on a stratified space? It's stratified BHV?
Yeah,
no?
exactly,
okay.
yes.
So what's the name of the... do you have a reference?
So I think it's often referred to as Sturm's algorithm. It's presented as a law of large numbers in the paper of Kallio Theodor Sturm on Fresheimian, on barycenters in spaces of global non-positive curvature, and there you can find it. And there's also or you can read up that there's also a book on convex optimization in Hadamard spaces,
Okay.
where we could also find more on it.
Nice. Thanks.
Other questions? Yeah, I have one. I did not completely understood in the example you showed. So, are your distribution really sticky, or how?
So
Because if you start with a finite number of samples, then almost surely they will that empirical distribution will have a Fréchet mean which is non-sticky.
No. I mean, the distribution has to be sticky. The way we define sticky.
But yeah, how do you? What is the distribution you started with in the examples? That's what
in the example. Well, I mean, this is a real data example. We don't really know what distribution these trees follow. I mean, you observe that the Fréchet mean seems to stick.
Okay,
there.
so
at least the
maybe
empirical
what
distribution.
you're observing is the finite sample stickiness
Yes.
rather than the real stickiness.
Yes, but that's exactly right. We of course don't know if the distribution actually is sticky, but we can still use these degrees of stickiness or these directional derivatives. They don't depend. Their existence doesn't depend on the actual on the stickiness itself. It's just that they convey how sticky something is if it's sticky. But you can still compute them and use them for inference.
Okay. Yep.
I'm not sure if you are starting from the phylogenetic tree as it is. Your starting point
Yes.
is the phylogenetic tree as it is.
What do you mean? I'm sorry.
Yes.
I guess.
Yes.
Short answer. Okay, thank you again to the speaker, and we're getting to the next talk.